right? When we talk about the Higgs mechanism, and up to now, we always had simple potentials so that you had one lambda coupling with phi to the fourth, and then whatever. Obviously, lambda has to be positive. This will dominate everything else, so if lambda is negative, right, the energy is not bounded from below, there is no ground state, you just keep falling into the abyss. Once I have, now imagine two fields. Let's imagine a simple example of, I remember there was a simplest discrete symmetry phi real, and discrete symmetry phi going to minus phi. I'll be sketchy here. I don't want to now give a lecture on this today, but still it may be useful what I'm going to say for the homework and more than that. So if I have two fields, discrete, I will have lambda 1 phi 1 to the fourth, right? Plus lambda 2 phi 2 to the fourth, plus lambda 3 phi 1 square phi 2 square. Let's imagine that there are discrete symmetries that forbid linear and cubic terms. I can always do that, you agree? So here I have symmetries, for example, phi 1 going to minus phi 1, phi 2, similar to the homework.
Yes.
And phi, okay, you get it. Now, I may ask, actually that down, I remember when I first started to pay attention, seriously, in the beginning, I was doing something in which I had to know the sign of this. You tendentially think that it should be positive. But when phi 1 and phi 2 are very large, they are going to dominate, unless they are very small. So, imagine that you have minus m1 square phi 1 square, minus m2 square phi 2 square. Now the symmetry is going to be broken. You have both quadratic pieces negative, so the second derivative is negative, therefore these are local maxima. Therefore we know there will be symmetry breaking, right? And then you can go on and proceed. Phi 1 is V1 plus H1. And you do the spectrum. And then we find out that you get one mass that goes as, you will get a sort of, you will get a matrix of it. They are going to mix. And the masses are going to look lambda 1 V1 square, lambda 2 V2 square, and then there'll be lambda 3 V1 V2, lambda 3 V1 V2.
But that's correct.
Okay? Sorry?
It is possible that I have also problems finding the symmetry remaining. But it's possible to have like symmetries between the two doublets, I mean the two triplets.
So the symmetries between the triplets are relevant. Look, those symmetries, discrete symmetries, they were only there to simplify the potential. You can forget about that. I'm interested in the gauge or global symmetry breaking. I don't.
No.
Of course, the discrete symmetries will be broken most likely, but there was not in the question.
Okay.
No, the question is only to know. You see, when I said the pattern of symmetry breaking, you have to find out that one guy is always in one direction. That's pattern means that you have to find out in which direction the second guy points. That's what the pattern means. You already solved the problem with one Higgs. The unique direction which preserved SO2. Now I have to see what happens to the second guy. And I told you it will depend on the sign of lambda 4, and you do these two cases separately and you may get it. Okay, try. I'll get hint by hint. If not, send me another message and I'll give you a little more hint, you know, at 2 o'clock or 3 o'clock or 4, whatever. So notice here, the trace has to be positive. So you will reproduce the thing that lambda should be positive. If V2 is small, you want this to dominate and so on. So we'll immediately see that lambda 1 and lambda 2 are positive. You will also see that lambda 1, lambda 2 minus lambda 3 squared, that the determinant must be positive. Which tells you that as long as this guy is not very large, it can be negative. Because they are going to beat him for large values of phi 1 and phi 2. It is bounded actually. You know, you are sure if your all mass is positive, mass is squared, if all mass is squared are positive, you will live in the minimum, that's for sure. Okay. But you don't know that it's a global minimum. But that may not be even so essential, okay? This is a side comment on physics. A beautiful, important subject of of cosmology, of stability of vacuum. I first studied by, I think it was Voloshin, which I forget now. And actually the theory, beautiful theory developed by Coleman, Sidney Coleman, in which they realized, these people originally, that you did not have to live in a global minimum. In other words, if the potential looks like this, and you are here, you say, oh my God, you know, I'm going to tunnel because this is lower. Well, it takes time to tunnel in quantum field theory. And obviously the tunneling, if you remember a bit about WKP, we have a digression here, obviously, right? This is not a lecture today, but just to wet your mouth a little bit. Do you remember the tunneling? It depended on the distance in quantum mechanics. Of course, it depended on the barrier. So it will depend on the, also on the difference of the vacuum, right? That's not surprising. It's not easy to develop analytic expressions, but for example, with a small difference here, when this epsilon volume is small, there is a beautiful analytic expression you can develop for the tunneling. By the way, now that we are here, it's better late than never. I was waiting for this question. When I taught you symmetry breaking, and I draw a case like this, then I said that there is symmetry breaking because you have to live here. I cheated. In quantum mechanics, what will happen? Not in quantum field, you will tunnel. Very quickly. You cannot live in one of the vacuum and quantum mechanics. It turns out that in quantum field theory, tunneling takes much more energy, whatever you want to call it, because you have to sort of, there is a whole space-time, you know, you leave your field in the whole space-time. I don't know how to say it well, but what we can show, to be sure, split it by epsilon, compute the tunneling amplitude per unit volume, somehow you define it the way you want, you will find out that it goes in e to the -1 over epsilon in proper units to a large power, maybe 4 or whatever. Exponentially fast vanish. When epsilon goes to 0 in the generate vacuum, there is no tunneling in field theory. This is why there is spontaneous symmetry breaking. And if you remember the double well potential, I wonder if you do, or maybe you never did it. Coleman actually does an example when you do the double well. Okay, it's a bit, you know, rough on the edges, but it's basically the same picture. Then the wave function is symmetric. There is no symmetry wave. The ground state wave function. So a key number of comments that I should now summarize to make it coherent. Typically we'll conclude when you study a complicated potential that self-couplings must be positive. This is not surprising because for very large values of the field this will dominate. The interaction couplings between two different fields or more may actually be negative in general. As long as the potential is bounded, which typically means, you see, if I take it to be negative, this starts creating problems, but when they are sufficiently large, they will win. You can play with it. Take some directions that you're worried about. For example, phi 1 equal phi 2 and very large. You will see that this will win. Actually, we write like this to make it simpler to study. Then you will see, well, let me not dwell too much. You will see in the homework problem that actually the sign of lambda 4 is allowed to be negative. If you thought that it had to be positive, if you think that lambda 4 is negative, then you should have concluded immediately a unique pattern of symmetry break. Because in order to minimize it, the rest of the potential, okay, now help. Phi 1 0 is 0 V1. I can write phi 2 0 is V2 0 cosine theta sine theta. Just to parameterize it. Why? Sorry. How did I put it here? By what symmetry?
SO3.
SO3. Now what remained?
SO2.
SO2, one of the directions I can put to 0 by that symmetry. So this is the most general one. So if you write your potential, the potential is function that I don't know how to write it. There is some function which is function only of V1 square and V2 square plus lambda 4 V1 square, V2 square cosine squared theta. This is the only piece that depends on that. If lambda 4 is positive, you will minimize it for, and so on. Okay. I leave it to you here. Think about it. But actually try to see what happens when lambda 4 is negative. I guarantee you that it's okay. Just as in this example, you will get everything under control. You see, if I'm right, then there should be something that depends on lambda 4 when it's negative, and the mass should go as minus lambda 4. So. Okay, maybe we stop here.
Okay.
Why is it so important? For example, imagine that tomorrow they find another Higgs, a bit heavier. Very unlikely the standard model Higgs looks more and more as the standard model Higgs when there is just one standard model Higgs. That's why we call it standard model Higgs. But if there were two, you see, I argue that by rotation, the doublet, I could have always taken in this direction. So you see immediately, I could always preserve charge. Even if I didn't, I would see it, okay. But it's simpler that I do it and I see immediately, then I define the charge as d3 plus y over 2. Now if there is another doublet, y prime, it's well, I couldn't rotate anymore. I've used my SU2 rotation. Just like one vector goes there, I can't put another vector there in general. So in general, there will be two web. And this will break charge now, because now I have a convention for charge, which I can never touch again. Okay, once it's accepted. Therefore, I have to assure that this is 0. Therefore, if there is a term in the potential that depends on the mutual, when I study the potentials, I have to make sure not only that I have consistent symmetry breaking with masses being positive, stable, minimum, but also I have to make sure the charge is not broken, because it's not broken. So this problem illustrates the issue that you face always in any physics beyond the standard model. I will give yet another problem of symmetry breaking. It's sort of a beautiful subject, and it's so important in our study of the physics of the standard model that it's first to learn it well. Although unfortunately in the standard model there is not much to learn. It's trivial, the example of symmetry breaking. It's just like this, almost like the real scalar field, right? So it happens.
Just a curiosity. In the second problem, when the vacuum manifold is an ellipsoid, that is not symmetric. That's symmetric. Why you can have like an ellipsoid for a vacuum manifold?
Well, I don't know what you mean precisely.
I mean, for example, when you get like a circle, you are sure that every direction is like equally.
Yeah, I'm not sure. Well, I'm not sure what you're asking me on the second problem. Let's discuss the second problem on Wednesday a little bit, if you agree.
Okay.
A little more. I don't wanna. Second problem is straightforward. It's long a bit, I admit. It's subtle, it's required some thought, but it's straightforward. You don't have to understand it in order to solve it. The first problem you have to understand, and then it's very easy to do it. The second problem is you don't have to understand it, and whether you understand it or not, it has some tedium to go through. Right? Okay, I've been pretending up to now that there was just one generation. Well, you were saying, what's a big deal? Just add more generation. right? If there is UD and they tell you that there is another generation that I call charm and stretch, add it. Let's talk about quarks only. Now, for some funny reason, let me do the following. Let me put a subscript here. Well, the funny reason is not so funny. I don't know whether these are physical states. I have to think a little bit. The physical states have well-defined mass. Okay, you and I are physical states because we don't speak of a linear combination of Borg and Julian, because you have, among other things, you have well-defined energy associated, static energy called mass. Because if I write this, if I Xerox copy my generation, and if I write the weak Lagrangian, right, the charged V currents, sorry, the W, when I say weak, I should be specific, then I'll have U, for example, UL bar, right, gamma mu, DL, plus CL bar, gamma mu SL, plus DL bar, gamma mu BL. And there was this, let's put, the states have this subscript 0 for the time being. I can write like this. This is G square root of 2, U, CT, 0, gamma mu. This is the same thing, you agree. There's a Hermitian conjugate structure sort one piece, okay? This is what I get. Subscript 0 just to, that's how I call them. Right? If I do that, then of course up quark couples to down quark, charm to strange, and so on. But you and I know actually that this is not the way it goes. Right? The flavor that we call, the species, they mix. How do I know that they mix? Tell me some examples that I know, or mixings. Between these funny objects, normal and strange and charm. For example, yeah, give me some process that you know of where there is mixing. Remember, just it's been some time. Alexei must have talked about this, right?
Yeah.
And even you know much more. I pretend that you don't, okay? It's always good to start from scratch, okay? And repeating. Modern psychology says that you to learn, it's good to, hear things repeatedly and repeatedly from a different perspective. Well, chaos can decay into pions. You can have processes like this. You can have K0 decays into pi plus plus pi minus.
Yeah.
I can go back even before there was charm and top quark. This we knew for a long, long time, okay? In the 50s when the strangeness were discovered, okay, very soon they learned. And then K0 and K0 bar can actually mix in finding those funny states with CP properties, odd and even, and so on. Okay, K0 has strangeness, K0 bar has opposite strangeness, and so on and so forth. So in other words, what was known, so this is what I have. In 1961, what was known is described in a famous work of Cabibbo, who said, I can parameterize everything. I can describe all the processes at that era simply by having this and he didn't call it Cabibbo angle, but we call it. This says if the weak current looks like this, then it describes successfully all the strange and changing processes. And the universal, in other words, strange and changing, there is a simple way of describing it where sine squared theta Cabibbo is roughly 1 in 25. I think it's around 13 degrees. Equivalent. So how in the world from here do I get there? Just to see what you remember. See, I know this is huh?
U and the doublet will be d cos theta plus.
Right, but why? Well, no, there's no theta here whatsoever.
Yeah.
I've just written my first generation Lagrange. You never objected, okay?
Yeah.
So then you say there is another generation. I write it down, and the third, and the gauge currents. The gauge interaction comes from the covariant derivative.
Yes.
There is no mixing in the covariant
The
derivative.
flavor eigenstates, but we want to write it in mass.
Right, but where does it come from? Flavor, this language that you use. You see, it's very easy to learn the language.
Yeah.
It's it's hard to remember where it comes from.
What is the question, sir?
Where does the mixing come from? There is no mixing here. I've written what I've written because it came. No, if I have a fermion, I write down this.
Because of the different masses.
I'm surely not going to get a mixing between three different states. You agree? One of the reasons, for example, just to tell you, if this is okay, what about photon? How does photon interact? For example, with up quarks. Is there mixing here? No, oh my God, this is the essence of QED, okay?
Yes.
There is no mixing whatsoever. The only thing that the photon does is get scattered off, okay? It makes no damage. It carries none of these funny charges.
Gamma 5 factor gives the mix.
Sorry?
In the weak interaction, the gamma 5, the off diagonal pieces.
Okay, what about Z? Or maybe you don't know.
No.
No.
Okay, let's, by the way, in order to motivate it nicer, okay, so what I want to motivate it, I'd like to make sure that then you don't forget this, what
Is it because the messenger?
I'm always scared that you learn something or the way I teach you, and then you get lost in the forest. There is so much information that we have to absorb. Okay, just to appreciate the point here. So in other words, I think this is what Vasily wanted to say. I could write a doublet like this.
Yeah.
It's kind of crippled. Where is its body? This was the picture, and they would write like that, okay? Now, suppose I take this seriously. I'm going back to 1961. Then how would the Z boson interaction look like? Remember, it had formed psi. There was this charge QZ psi with gamma mu. Maybe we write it here. This charge is not so important. What is important that the D and strange, what do I mean by new generations? Okay, they have the same quantum numbers. This is a strange thing about the world in which we live. The repetition of what world is made of, okay? If we were not restless to do experiments, by breaking things apart, we would never know. We would only think that there is only this first generation, okay? The things about generations when we add them, okay, they are exactly the same. They only have different masses. They are the same particles. So that means that QZ of down quark is equal to QZ of the strange quark. Whatever it is, compute it, I don't care. What I will get is Z mu. Then I will get, you see what I will get? I have this state. I will get D bar cosine theta plus S bar sine theta, gamma mu. Then the charge, I'll take it out. And then D cosine theta plus S sine theta. That's it. And the charge would be minus a half, right? The lower component plus 1/3 sine squared theta w. Some number. Look what we get. We get Z mu, D bar D, cosine squared theta, plus S bar S sine squared theta, plus cosine theta, sine theta, d bar s, s plus s bar d. I took off gamma mu. Just I want you to see the flavor dependence, the theta dependence, not the Lorentz structure, okay? So, okay, this is, it would look like this, but notice something strange here. Why do I call it strange? This strangeness is violated here. In other words, I could have the following process. Z boson, D enters, S come out, D enters, S come out. Right? Because I can make D become S.
Yes.
I'll do it twice. This will change straightness. Agree? I'm just exchanging. Z boson couples to D bar S, but also S bar D. And what I have here is CS and CS. Cabibo. Right? CS. This is Cabibo. So, this is why I'm giving you time to think where the mixings come from. If you remember, if you manage to recall, okay, or look it up or whatever while I'm doing it. I want to tell you something else, the importance of this mixing and the importance of having charge. So what would I would get the amplitude for this process that I could write, there will be G squared over cosine theta W, okay, the usual cosine squared theta W, mz squared at low energies, right? I pinch the propagator, okay, low energy. What do I get? I get S bar, and I can write the whole Lorentz structure, but just to emphasize it, S bar D, cosine squared theta Cabibo, sine squared theta Cabibo. Let me not write cosine squared theta Cabibo, it's basically 1. So the amplitude, I can call it effective Lagrangian for delta S equal to would be this. This I call G Fermi, remember? This is MW squared. There are factors of 2 and so on. This will be G squared Fermi S bar. And let me write it, there will be S bar gamma mu LD if you wish. It will be left-handed. Or, I'm sorry, there is actually hidden A plus B gamma phi. The important thing is that there is gamma phi. By the way, the mixing is there independently whether there is gamma phi or not. Even the structure, Lorentz structure is not there. Okay? But in general, I will have this, okay, square. What would this cause? Notice that I could sandwich between K0 and K0 bar. Okay, I always remember, but I forget, but we can reproduce it. What is K0, what is K0 bar? Okay, in the oxide picture, you have a triplet of pions, then you have a doublet K0, K plus K0. You remember this forms a doublet under isosymmetry. What is K plus? It must have U quark.
US.
So it must be US bar. So K0 must be DS bar. That means that K minus is U bar S, and K0 bar is D bar S. So because this, remember there will be also Hermitian conjugates, so I don't have to worry about the order. I can then make K0 become K0 bar in a static Lagrangian, I will get K0 G Fermi over square root of 2 sine squared theta k vivo S bar gamma mu A plus B gamma 5D times S bar gamma mu A plus B gamma 5D times K0 bar. Now, how would I compute this? It's a very non-trivial thing to compute something between two mesons. There is strong interactions, okay, I'm at low energies. I don't know how to compute it, okay? These people use lattice and so on. But there is a sort of suggestive trick to say, when I compute it, I can compute this by inserting a sum of all the possible states in this space, which will be vacuum, pion states, kaon states, 2 pion states, and so on, okay? This is one. Okay, the usual trick. And then the sort of feeling was, and I don't want to enter too much into that the vacuum ought to dominate, okay? That it will give the dominant more contribution than a pion state and so on. Not very convincing, okay? It's called the vacuum insertion approximation, okay? So let's just try it. So let's just say that the state that dominates would be a vacuum. It costs you sort of less energy to go through the vacuum than the more complicated states. Then we will get K0 S bar gamma mu A plus B gamma 5 vacuum S bar gamma mu A plus B gamma 5 K0 bar times G Fermi over square root of 2 sine squared theta k v. Now this thing, two things. This is a pseudo-scalar. So which current can, and this is of course a scalar, which piece can contribute? So maybe this is what you maybe remembered, okay, gamma 5 is very important in order to get a physical effect. But the flavor change doesn't care what kind of currents you have. They may be axial, vectorial, whatever. But this sandwich, only this piece contributes. And that's important. The pseudo vector will contribute. The vector will not contribute because you have to change the property from scalar to pseudo-scalar. Okay, it cannot be done by a vector. Okay. I'm not really teaching this. So this piece contributes. And this here, I think you should have discussed this in the pion decay with Alexei. You computed pion decay with Alexei? So how does pion decay? It's what you have to connect in the case of pion with a vacuum, if you remember. And then there were leptons. Right? When you remember that?
Yeah.
Well, if you don't, this is how you did it.
Yeah.
These things here.
Well, introduce a number times the momentum.
Right.
Yes.
Because you say Lorentz structure tells me this is going to be proportional to the momentum if it's not zero. Very good. Right. So this is Fk. He called it F pion.
Yeah.
This is a kaon decay constant. This measures the possibility of kaon decaying into whatever it has to decay. The way pion is F pion. Okay? And it's at the order of 100 MeV. Now, depends how properly normalize it. Okay, so there are some various definitions. Times P mu. There is a normalization of this state to keep in mind. Okay, I'm glad that you remember that. This is important. We will redo the pion decay one of these days. And I tell you why it's important to rethink about it. So I would get that K0, this effective Lagrangian Hamiltonian delta S equal to K0 bar is non-zero, and I can estimate this GF over square root of 2. I write because I didn't write any factors. Okay, it's funny. Sine squared theta. And then there will be FK squared. You agree? Then because of P mu, all you have to use the fact that P mu is MK squared. Now, this is a static energy. This has a dimension of mass. Actually, there is a normalization of K0, which is 1 over square root of MK. But dimensionally, I know that has to be of this form, because it would come out wrong. This is 1 over mass squared. This is mass squared. Fk has a dimension of mass. Decay constant. It's a dimension of mass. So this will not go as mk squared, it goes as mk, if you wish. And the reason is that this state is 1 over square root of mk in the normalization. Strictly speaking, is like this. Okay, I took some time. I didn't want to just cite it, I just wanted to remind you, okay? I imagine he discussed that, let's say.
Yeah.
Okay, so it's good, however, to remind us. So what it means that if I look at the mass matrix between K0 and K0 star, which is MK, these are particle, antiparticle by CPT theorem have the same mass. This can be verified to an extraordinary precision. Call it MK bar if you wish, just to understand. MK bar minus MK divided by MK is less than 10 to the minus 18, according to PDG. Okay. So we'll take it to be equal. However, there is a mass difference between K and K bar. This is very important. They are not eigenstates. How do you know they are not eigenstates?
K.
K0 and K0 bar?
Yes.
Well, you can think like this.
Yes.
CP is basically a good symmetry. It's violated so feebly. I can pretend it's a good symmetry. Except when I study CP breaking, okay? It's one of, like neutrino mass. For all practical purposes, neutrinos are massless, except when I study their mass, okay? So CP tells me, and they transform into each other by CP, that they cannot be mass eigenstates. The mass eigenstates must be, call them plus minus, K0 plus minus, K0 bar, over square root of 2. When I write the states, I'm sometimes cavalier, I put a bra, or I put a cat, or I write like this, or I may write, okay, you understand what is going on. That, of course, is equivalent to the fact that there is delta mk here, delta mk here. There must be. This matrix, this symmetric matrix, has eigenstates 1, 1, and 1 minus 1. This is not the difference between these two states. It's too small. Look at this matrix. What are the eigenstates here? Act on 1, 1. What do you get? mk plus delta mk. Acting 1, 1. If I act on 1 minus 1, what do I get? I get mk minus delta mk. 1 minus 1. Agree? This is this k plus when you normalize 1, 1. So you can see these are just the coefficients in the brass. So the mass difference, the delta mk, is precisely 2 delta mk. But what is delta mk? This is delta mk. This is a static energy which is a mess. I can do it, and we will compute these things for zero external momentum. We actually have famous box diagrams that we have to worry about. Okay, this is how you do it in the standard model. Okay, my static Hamiltonian effective sandwich between the states is precisely what will produce this off-diagonal master. That's how I have to interpret it in the limit of zero external momentum. So I can compute it. What I want to tell you, that this is called a vacuum insertion. This is a bit sort of hand waving, okay? It has been done to extraordinary, by different techniques, okay? The MIT bag model was used and so on, and these days on the lattice. And it works pretty well. It's not perfect, but it works pretty well. What will we get? Let's estimate it. What will we get for delta mk over mk? G Fermi over square root of 2. That's, I put everything in GeV. This is 10 to the minus 5. Okay. Fk is roughly 100 MeV. So I get 10 to the minus 2. And sine squared theta capivo, I'll take to be 10 to the minus 2 to help myself, okay? Because what I know experimentally, that this is a small number. This is experiment. And I'm far off by 4 orders of magnitude. This was a... so we had two questions. How in the world do we get the mixing? And the second, how can we tolerate this mixing? This mixing is a disaster. Because it creates a k-long k. You know, when you say maybe your calculation was not so good, but not 4 orders of magnitude. You see, I didn't worry about factors of 2, and I didn't put a pi. Maybe, well, it's a 3 level, there's no pi. And it's a kind of nice thing because I have to produce the mixing and I have to then to kill it when it damages me and keep it when it does good for me, okay? There is a little magic in what the mixing is. That's why it's worthwhile teaching it seriously, although it's a sort of trivial thing that there is some angle between the generations. It was this sort of, it rang the bell, you kind of remembered what Alexei taught you. Okay, I wanted to refresh your memory. The problem was, first I put the mixing by hand, kind of. I didn't yet understand where it comes from, but I know it's there. Capivo taught me. In 1964, Gleshow and Bjorken, one of the fathers of quarks, if you wish, with Zweig and Gell-Mann, actually, maybe the most important contributors are Bjorken and Feynman, with Parton, but especially Bjorken can emphasize the scaling. They suggested that the world would look more beautiful. You see, there was up quark and then 2 down quarks. They say it would look more beautiful if it was another up quark. Let's call it charm. So I did a charm quark, 1964. And this is very interesting, okay? I'm fascinated by the irony of history, of development of physics, okay? But nobody paid attention to Gleshow when he wrote his beautiful paper in 1961, and I guess he didn't pay enough attention. So he completely ignored the work of Gleshow and the standard model and the implications. He just said, with Bjorken, it would be nice if there was another generation completed, so there's a charm quark, okay? It will take years later, 1969, Jim Gleshow, in a great work, Iliopoulos, Greek physicist working in France, and Mayani. They were postdocs at Harvard. Leopoldos in Paris, Mayani in Rome these days. Realized that if you had a charm quark, then it would couple to the orthogonal state. Before this paper, 1969, people have no idea how to treat the force, okay? If you look at the Weinberg's beautiful, great work, 1967, it's called the model of leptons. There's no idea because he's deeply aware of this problem. And I guess he didn't pay attention to Bjorken and Gleshel, okay? You see, if I have this, and that would be logical, I have to prove it that this would look like if I have two generations, what will happen? That the interaction I produced will happen from here, chin. This gave me cosine theta, sine theta, d bar s plus s bar d. Agree? What will I get here? Minus sine. So what plus, let me write, plus cosine squared theta, d bar d, plus sine squared theta, s bar s. Cavill. To be sure that there is not a mixing, weak mixing confusion. Here what I will get will be minus cosine theta cavivo, sine theta cavivo, d bar s plus s bar d, plus sine squared theta cavivo, d bar d, plus cosine squared theta cavivo, s bar s. This terrible thing disappears. This is a solution to the celebrated problem which is called the flavor conservation in neutral currents. When you write the neutral currents, the current of the Z boson or the photon, they conserve flavor. Photon and Z boson cannot change flavor. They would give you immediately too much. A photon would be even worse because mass is small, but even Z boson is a disaster. It produces a tremendous amount of change of flavor. I could live, for example, if one day there is a very heavy new gauge boson that does that, you and I could live with that, as long as it's very heavy. Because when I got G Fermi, this was G squared over mz squared. Some new Z prime, okay. As long as, then I'll make it very heavy, okay. But not in the standard model. And so two things work. And then you get, when you sum these things, you just get d bar d, and this is how actually it looks in experiment, okay? It works, beautiful, okay? Adding this guy solve the problem, okay? And it's very interesting, this design for beauty, for aesthetics, for symmetry. Okay, once again, the symmetry argument. The last 30, 40 words, 50 or more development of physics were all based on the success of symmetry. Pushing it as far as possible, but you can imagine that, you know, it's remarkable that such arguments work. So I need a charm quark. And because I need it, I added it. And I know. Okay, I want you to tell you, I needed it. It wasn't that charm existed and you wrote this, okay? No, it's the other way around. The theorists postulated the charm quark and showed how it would actually work. The question is, however, is where do I get the mixing from? You still don't tell me. I have to produce
The coupling to the hits, the Yukawa.
to your cows. So let's see that. But I pause here just to see, okay? That was a little quick because it was a reminder. In what follows, by the way, I want to justify this. I want us to reproduce it for us, although it's highly convincing. Okay, I will erase this. By the way, K plus and K minus are not eigenstates of mass. Because CP is actually not a good symmetry, okay? We'll have to remind ourselves from time to time. How do I know that CP is not a good symmetry now while we are still thinking how to proceed? How would you check CP? Well, you have to know something important. That K plus and K minus actually have very different lifetimes. This guy is short-lived, this guy is long-lived. K tau short is about 10 to the minus 10 seconds. Or we often say that it's about a centimeter. You will hear us speak, okay? We talk of lifetimes in centimeters. You know, we do it. And you remember tau long in this? 10 to the minus 8 seconds. It's about a meter. So now that you know that they lived very differently, how would you check CP violation? Beautiful experiment by Fitch, Cronin. Okay, if CP is a good symmetry, help me, what does K plus decays into? Yes, pi plus, plus pi minus. CP even, this is CP even because I have two guys that go each other, or pi 0 plus pi 0. What about K minus? 3 pi. Pi plus pi minus plus pi 0. So what I have to do, I just have to wait. I produce, I don't even know what I produce. Who in the world knows in the strong interactions? I probably get some mixture of the two guys because strong interaction don't care about what I'm doing here. They produce some well-defined strangeness, but I just wait. Or I put a mine detector a meter or 2 meters or whatever away, and all these guys will disappear. They will decay, all of them, exponentially fast. So what is remained is this. And what he found out is that K minus decays actually into 2 pi also, but 1 is 1,000. So in other words, K long is K plus a bit of K minus. And K short is K plus. K long is K minus plus a bit of K plus. Right? This epsilon is what? It's 10 to the minus 3. Because if K long has K plus 1 in 1,000, then it's 1 in 1,000, I will see this guy decaying. Okay, just a reminder how but what I'm going to do, as long as I'm not pushed by whatever I'm doing, I pretend that CP is a good symmetry to simplify our life. And then, of course, I ask the question, how do I account for that? Because it's small. This is not a weak interaction process. It's extremely weak. 1,000 times weaker. Very different from parity violation, which is maximal, which happens all the time. Okay, so what Guillermo says, I should look at Yukawa interaction. And Yukawa interaction, in other words, would be in the unitary gauge. Remember, it was dl bar, for example, Yukawa d. Let me write like this. Yukawa d Vr V plus H plus 4 other quarks. Okay, let's just look at one species. Okay, so what is the point here? Well, I have more, but by the way, I should put this subscript 0. This is how I call these guys. Now, the rule of the game that guarantees normalizability according to et Hoff is you must write down all the possible dimension 4 terms and less. So that means that I can mix any down quark. The notation is a bit confusing. By D0 I mean down strange bottom, okay? So Di is down strange bottom and whatnot. And that means that what I have is a matrix of all possible couplings, right? There is no symmetry. It would be a miracle that it came out diagonal. Because there is no difference for Higgs, if you wish, in other words. Higgs cannot distinguish. Because gauge boson did, because gauge boson came from the covariant derivative, which only by definition coupled down quark to a down quark, okay? But the Higgs says, just give me anybody with the right quantum numbers, and I will couple to it. As long as these objects are massive, or potentially massive. Okay, well, you know this story, but I need to refresh your memory. I'll come back to this. We have one lecture on kaons just to sort of cement your knowledge. So in other words, what I get is a matrix. So let me write it like this. I don't know how many generations there are. Then this Yukawa D would be a matrix, which I'm going to call MD. MD Ij is Yukawa Ij times V. Times dr sr vr. Okay. Plus h over v. I took v. Okay, you're following me? All of you? I'm going to write it as dl bar, sl bar, bl bar, uld dagger, md, urd, dsb, 1 plus h plus v. What I've done, I've changed the basis. I've introduced d, s, b, lr. I call uld, dsb, left, right. This was the subscript 0 originally, okay? These were my we call them flavor states or weak states. Weak states, sorry, it's the correct name. They are not mass eigenstates. These particles are not well-defined particles because this is a matrix, right? The new states will be physical particles because I will use the freedom of UN and UR to diagonalize this. And non-singular matrix can be diagonalized. When it's Hermitian, then left and right are the same. When it's not Hermitian, then you need more. M is not Hermitian in general, so UL and UR are different. Remember, they must be unitary because I want to preserve the kinetic energy, okay? You remember this? Okay, good. So the flavor mixes is hidden in this. ULs. Or good. I'm glad. Which means that the weak interaction becomes G over square root of 2 U C T bar U L U dagger ULD gamma mu DSB W mu dagger. Gamma mu is another space, right? It's a Lorentz space, so they commute. And this is called, it's a unitary matrix which is called CKM matrix. This is a celebrate Kabibo for 2 generations. It was called Kabibo. And this is called VCKM, Kabibo Kobayashi Maspara. We reproduce the celebrated result of Kabibo, flavors mix. In general, this is non-diagonal, of course. What about Z and the photon? Remember, in the case of photon and Z, or any such neutral gauge boson that couples at psi bar gamma mu some Q psi, the characteristics of QA and QZ, remember that they practically have the same quantum numbers. For example, if I isolate here down quarks, then I would have DS, BL, ULD dagger, ULD, DSB. You see, I cannot, in the neutral sector, I can never produce the mixing because I will get U dagger U, as I get here. The only thing is that I have different species, okay? So the only reason there is mixing in the W currents is the W takes up quark into down quark, and they, of course, will not diagonalize the same way in general because their mass matrices clearly are not related to each other. Look at their eigenstates, eigenmasses, they are completely different, right? They have no indication of being similar. Okay? So this gene form follows immediately, okay? This is one. As long as all the down quarks, for example, A is universal, or Q down quarks, Z is universal, which is true. So introducing the charm quark, if you wish, completing the doublet structure. You're saying, but it's so obvious that you should complete the doublet structure. It seems so obvious, right? I mean, that's a structure. We know now. Forget the flavor violation. Actually, we know there is something called anomalies that maybe we even managed to study a bit towards the end, let's say, that are very bad. Field theory, which has anomalies, is bad. And that requires actually that you must have the doublet structure, so it happens, which is obvious, kind of natural, right? How can I have half a doublet? Right? U down and then S by itself. Then I tried to mix them, but there was something crippling there, okay? There was something incomplete there. It took courage, effort, and deep thought to arrive at that. And as usual, this is what you will learn when you look back 20 years later. The easy things are hard. The simple, these basic breakthroughs are somehow hard to get. Whatever it is that makes us resist this. Now, what we have to learn now, because this is unitary, VCKM, and it's an n times n matrix. So how many angles it has? Okay, I divide the unitary matrix into angles and phases. What are angles? Well, when I'm in a real situation, then unitary becomes orthogonal. How many are mixing angles in orthogonal matrix? SOC has 3. SO2 has 1. One half n n minus 1. Number of generators. Remember, the generators are anti-symmetric. So it's 1/2 n n minus 1. So it's a convenient way to separate them because it's a sort of the real variables, and I want to know what is complex really, what is real. Okay, and so how many phases? Well, n plus 1. Because unitary matrix has n square elements, not 2n square. An arbitrary matrix has 2n square real elements. But because of n square conditions of unitarity, okay, you have n square elements. So for example, if I take one generation, how many phases? How many angles? 0 angles. Well, obvious. How many phases? One.
One.
Let's see. By the way, I wrote only the down quarks. You would do the same thing for the up quarks. Actually, we do the same thing for leptons, so you have to think about leptons. But Alexei prepared you for that, so I just have to refresh your memory. I noticed that there was always this factor. I forgot to emphasize 1 plus h over v, whatever I write. So when I diagonalize here, then Higgs coupled to the diagonal thing. Higgs does not change flavor. That you can remember as a rule of thumb. Neutral guys do not change flavor. Because in the process of diagonalization, you also diagonalize its coupling, okay? So Z boson, photon, and the Higgs do not change flavor. It's only crazy W, because W mixes different species. This guy doesn't. This guy takes down quark into a down quark, just as W and Z. So in other words, and what is that phase? Well, G, e to the I theta, U bar, gamma mu D, W mu plus. Is this a physical phase? No, I can change the phase of a down quark. And of course, look, there is also, let me write it, there is M up, U bar U, plus M down. I've diagonalized as D bar D. This is UL bar UR, plus UR bar UL, say. So when I change the phase, I can now say that DL, e to the I theta, is DL prime. I have to do it in the right-handed sector also, because I already use my freedom of masses. They are real positive numbers, okay, in the process of diagonalization chosen. So, I'll comment on that in due time. But I can always do that because the right-handed quarks do not enter into weak interaction. So that's a better that I have to change their phase, okay? I can freely change, I can do anything here I want. All I have to remember, do it in the right-handed sector. You see, if, just to tell you, suppose there is another W which couples to the right-handed quarks, then I better be careful. Maybe I'm producing a phase there, I don't know. Okay. And in Sander model there is no worry, because Sander model is crippled. Okay, it's completely, right? Okay. God is invalid according to the standard model. The couples only two left. So I can, this phase is not physical. What about two generations? So actually there is no phase. But how come there is no phase? I just counted the phases. Well, there is no phase because the number of phases is not what I count. The number of phases is what I cannot eliminate. There is a profound difference between phases and physical phases. Okay, physical phases is whatever remains after you use all your freedom. So you have to be very careful when you do that. N equal to has one angle, theta caviva. How many phases? 3. Are they real? No, you can do the same thing I did here, but I won't do that. I invite you to check that. Instead of doing that, let us, you and I, think of it. Let us decide what could be physical and what could be not physical. And that's the following. I was a bit careless when I counted that, because I forgot that I can transform. I can keep doing this. I can make these changes, you agree? Or when I use it. And then DL, I will do the alpha D, DL. By the way, you should then do the same thing for right, because you don't want to change your mass terms, okay? You made them real and positive, okay? But they have no weak interaction, so I stop writing what we do to the right-handed quark. just a reminder, SL goes into e to the I alpha SSL, BL. So how many of these phase freedoms do I have? 2n. So what is the number of physical phases? Well, it's 1/2 n plus 1. So I'm calculating the number of physical phases, those that will not go away. Minus. I'm going to get rid of these 2n phases. So now how many do I have for n equal 2? Well, I get a negative number. I'm okay. There are no phases in n equal 2. What about n equals 3? Six minus 6 is 0. Oh. But I need a phase. Okay, why am I bugging you with that? Because CP violation means there's something complex, okay? We can remind ourselves of that. So I need a phase. But I just got rid of that. But it's funny, something is wrong, because Kobayashi Maskawa actually introduced the third generation. When they saw Jim having courage to say there is another quark, they were brave. And they said we led another generation to get a phase. They knew that there was no phase when n equal 2. And I'm sure they didn't just do the counting, we all knew. Sorry. I got 0, so what's going on? How many phases? Actually, it's claimed by Kobayashi Maskawa in their paper. They claim that there is one phase. It's a featherweight Kobayashi Maskawa phase. So I've done something wrong. Look. I can do the following. I can write this. I should have given me this alpha c. I could have written, okay. Alpha c I can write as, okay. Sorry, let's write like this. E to the I alpha c. I can write e to the I alpha u, e to the I alpha c minus alpha u. Okay, not very smart, but e to the I alpha t, e to the I alpha u, e to the I alpha t minus alpha u. Alpha d, e to the I alpha d, I write as e to the I alpha u, e to the I alpha d minus alpha u, and so on. Okay. Notice that then there will be an overall phase here. So in other words, what I'm doing, all the up quarks have one overall phase, all the down quarks one overall phase. But look what the VCM is UL up dagger, ULD. This phase does not exist, this phase. There are no 2n freedoms. You see, it's very subtle, okay? Whenever if you were to study CP violation, and whenever you have to do with symmetry, there is no simple rule of knowing. You have to be smart, sort of, and be careful, and keep thinking what really remains, okay? I told you that I once spent a lot of time computing 0, because I didn't do this. Well, I couldn't see that this could have been done. And this won't happen to me again, you know, I'll do everything not to. You learn a lesson, you get burned, normally. So I miscalculated. I should subtract 2n minus 1. There are not 2n freedoms. Well, actually there are, but one is overall. And overall makes no impact. An overall phase will cancel between bar and the. So now notice. Oh, sorry, why did I? I feel like, you know, Control Z. I don't understand. Now for n equals 3, it's okay. I get one phase. This actually is 1/2 n squared plus n minus 4n plus 2. And this can be written as 1/2 n minus 1 n minus 2. 4 minus 1 is 3, precisely. Okay, this is the number of phases. And I've now really used up all the freedom, okay? I cannot do better than this, but I cannot do worse than this. So what I've learned is that I'm going to ask you for a favor to stay on another 15 minutes. We spent some time discussing the homework. Also, we almost made up the lecture that I'm going to lose. It's okay, just a few times, 15 minutes longer. 10 minutes longer and we'll make up. Next Monday probably I'll be away. I would encourage you to check that, okay? I guess you did it maybe, Alexei, if you get it. It's just an easy exercise.
Yes.
So you see that you can eliminate those phases, okay? Now why is it that you cannot do it in the, let's try to see what's so different in 3 generations. So once again, this and n equal to VCKM is O K-vivo. It's a rotation. Cosine theta K-vivo, sine theta K-vivo, minus sine theta K-vivo, cosine theta K-vivo. One thing to stress, maybe I cannot overstress, but you may be familiar, that the physics of mixing depends on the relative rotation of up and down quarks, as you can see here. Which means that you can choose any basis you like. You can say, oh, I like to work with up quarks which are diagonal. Then all the mixing is in the down quarks. That's equivalent to saying, I can call this VCKM. People often do that. Or I can call this 1 and call this VCKM dagger. I have no way of resolving this, right? There is ambiguity. I tell you why I'm saying this. You hear this very often. That we would like to, that we would ideally like to predict these mixing angles. Sounds noble. I'm more and more pessimistic. Okay? I spend a lot of time. More like 30 years ago, but a lot of time. And then Enrico Wolfenstein, who was my age today, a little younger, distinguished physicist, they came and collaborated with a friend, was telling me it's a waste of time. This is like computing distances from planets. Okay, it won't be done. But I want you to see, if you want to compute it, and suppose you want to compute it and you have a standard model like physics, then you see, it's a very dangerous statement because what could you compute? If you tell me I compute the mixing of down quarks, tell me which basis. And how do you know that you have a theory? Whatever, if you suppose you compute this and compute this, I'll never be able to check that. Because this funny guy W is user unfriendly. He doesn't care that you computed this. It only depends on the difference, okay? So if I want to compute this mixing angle, what I need to do is find a new theory beyond the standard model, then it becomes meaningful, in which there are new interactions, which just depend, for example, on this. For example, grand unification has that. You have new X bosons, they depend only on this mixing angle. Aha! Now your theory makes sense, because you say, I'm going to predict mixing angles, okay, that's how you would do it in proton decay tomorrow, in some new process. But you can't do it in the W thing, because it doesn't depend on the individual mixing angles, okay? It's very important to think what you mean by predicting something. So n equals 3. It's now VCKM. Okay, I think I can erase it. All the tail, all we have to have the definition that the weak Lagrangian G square of 2 UCP bar gamma mu VCKM DSB. I was very unhappy with 3 generations, okay? I didn't like that from the beginning. When I studied my PhD, I was fascinated by the problem of CP. And there were 2 interesting roads to take. One is by Kobayashi Masukawa, who said there is another generation, but that to me was trivial. There was no new dynamics, no new physics, just the same Xerox copy of the previous 2 generations. Okay, there was a phase. At the same time, Mohapatra and Patti said that imagine that besides WL there is WR. Only 2 generations. Imagine this left-right symmetric world, okay? For 2 minutes. Then here you would have Kabiba rotation. You will do it by rotating those angles. But here now, when you make this real, you don't make this real. No a priori, not for any reason. You're making these rotations to get rid of these phases, but you have to simultaneously make rotations. So even with 2 generations, Mohapatra said, and Patti, that epsilon CP in this theory would be MWL over MWR squared. If this mass goes to infinity, you're back to the standard model, there is no CP violation. Okay, you don't have to learn that, but and then this would depend on sign of a phase, and they showed it in the right exactly. You couldn't eliminate simultaneously left and right. You see, in this left-right symmetric theory, the left-right symmetry is broken. The world is not left-right symmetric. You and I do not live in left-right symmetric world. It may be at high energies we do, but surely today we don't. So what is the beauty of this theory? Parity is broken because WR is heavier than WL. So the maximal amount of parity violation, near maximal, because WR is heavy. But because WR heavy, CP is weakly broken. So you have one and the same source of both symmetries, new dynamics, a beautiful left-right symmetric world. And you would get the upper limit, MWR, less than about TV, because this has to be 10 to the minus 3, and this is less than 1. You have an upper limit on WR. People often say, you know, that beautiful ideas somehow have their beautiful pictures, beautiful theories, are the reason, the threat for their existence. I'm not so sure. I find this time infinitely more beautiful than adding another generation without any non-trivial dynamic. But this is not the way it is. There are actually 3 generations, and WR, if it exists, I still like to believe, is heavier than now about 4 TV. The CP violation has nothing to do with beyond the standard model physics. There is strong indication that all of it comes from Kobayashi and Masukawa. And this is really some of the standard model resist change, okay? Driving us crazy all these decades. So how would I write VCKM? Well, I have 3 Euler angles. So I rotate by say around the 3rd axis. So I call this cosine theta 1, 2, sine theta 1, 2, minus sine theta 1, 2, cosine theta 1, 2. See, in 2 generations, this is basically what do you call the Kabiba angle, do you agree? 1, 2 is just to see which way are right. There are 3 angles, I will call them 1, 2. Well, it will be clear, and you maybe remember. If there is a phase, I better put it here. Because here, when I am near the end, I can use the phase freedom of these guys to eliminate, okay? This is why the phase exists, okay? Here we would rotate about this axis, say. So how I'm going to call it? Cosine theta 2, 3. Thank you. Sine theta 2, 3. Minus sine theta 2, 3. Cosine theta 2, 3. Here I'm going to rotate here. Cosine theta, what is this? 1, 3. Sine theta 1, 3 minus sine theta 1, 3, 0. I put a phase here. This is not the original. I think it's like this. I think that's the convention. This is the sort of the PDG uses this almost everybody, okay? This is used to my friend Kyung, my collaborator, and Chow, Lindley Chow. He spent a lot of time thinking about. I should look for my glasses, but I hate to do that. You have the CKM in front of you, no? Well, yeah, this is the PDG one, I don't know. I think I'm right. Okay, help me. I have to find my glasses, I know. Maybe that's big enough. That's how they did it, right?
Yeah.
Okay. No, just to be sure that we have the same thing.
Yeah.
Yeah, e to the minus I delta and minus e to the I delta. Thank you. Let me just keep it. So it's not surprising that you cannot get rid of it, okay? Because it's buried. It's far. You want to put it as far as possible from the.
What happened to the last cosine?
Sorry.
It's
Cosine.
There's a matrix in the middle of the corner.
In the middle, maybe I keep it. You're saying cosine theta 1, 3. Thank you. Now, what we know is very interesting, that basically there is no mixing, okay? Again, like CP violation, unless you're studying mixing, you can forget about mixing, okay? Theta Capivo is at 13 degrees, the other guys are basically 0, except that when flavor changes, they're important. Theta 2, 3, there is a next neighbor approximation. This is about 10 to the minus 2, maybe factor of 4. And theta 1, 3 is 10 to the minus 3. So you like just to couple to your neighbor. And second and third generation basically don't mix.
And the phase?
Phase is large, I don't remember, around 40 degrees. It's not small. Why? Why? Notice when we look at this. Take theta 1, 3 equals 0. Then you get immediately that there is no phase. I mean, it's there, but it's not there because, well, you said because you put a phase there. What happens if I take theta 1 to equal to 0? Maybe then the phase is there, you say. Okay, this will be 1, this will be 1. But notice then, I wouldn't have this. So now I start to use freedom of the quarks. So what it means that freedom, that I can multiply, for example, one column or one row by phase. That's just the overall phase. So what I'll do here, let me multiply by this, by e to the I delta, this column. What happens? This goes away, but I get e to the I delta here. Now I'm going to multiply this row by e to the minus I delta. And I got rid of the phase. And this is just going to be the overall effect that will cancel, okay? E to the minus I delta times e to the I delta. So there is no phase. And you can easily check when theta 2, 3 is 0 by the same argument. So you see, the CP violation, that's another beauty of the standard model. You don't have to assume a small phase. It's automatically small. That's a prediction. Flavor mixing is small. I measured that before. I found out. Then I predict the CP violation will be very small. It looked even it looks too small because it must be proportional to theta 1, 3 or sine, where they are small, theta 2, 3, theta 1, 2, and delta. And this must be 10 to the minus 3. It looks too small. There are some enhancements. For example, this by itself is theta 1, 2 to the minus 3. Okay. Now, various enhancements that enter, you can imagine. For example, if there are only 2 generations, again epsilon CP is 0, that means that you are going to get an enhancement. This will depend on the top quark mass. And then, you know, now it has to be how it goes, with what coefficient, right? MW and B, I don't want to, there'll be various coefficients. It gets enhancements, okay? You have to take my word for it. I'm not going to compute this, okay? This is a lengthy and not so illustrative process. It comes out okay. Not only that it comes out okay, it describes all the CP violating processes. Chaos, B physics, charm, you know, one in the same phase, so we like that. For example, if I had 4 generations, I mean, I know it sounds strange, okay, people used to make fun of my dislike of 3 generations. I was hung up on 2 generations, you know. When people come to my age, they tell you that the world was better then. Most of the time, you know, parents, grandparents, they tell you everything. You know, young people are better behaved, girls were nice, whatever you would say. Music was better, movies were better. Actually, my daughter claims that movies and music was great at my time. She's crazy about, you know, the Beatles, Moody Blues, Rolling Stones, whatever, all that. Then one thing was better, there were only 2 generations, okay? Then I guarantee, okay, you could just remember one, you know, I can live with this so easily, I can estimate everything now. You are not going to write this, you know, and you get this mess that you don't ever want to remember, right? I hate it to this day. Whenever I work on something new, when I first pretended there are 2 generations, I give you strong advice. Actually, some years ago, we came a nice paper in grand unification, and one of the ways was we just wanted to see what happens with 2 generations. And it became an important paper because we could solve analytically what goes on and then do little perturbations around it, okay. To understand the mixings, go back to 2 generations. And you will see today there is not enough time, we are about to wrap it up. Did someone have a question?
Yes. I didn't really understand how you remove the phase when you multiply the row by e to the power I then the cos.
Well, if I multiply by row and the column, row is, one is up quark and there is down quarks.
Okay.
Then the effect will cancel. E to the I delta times e to the minus I delta.
Ah.
It will be an overall phase. It's not, you see, whatever is overall, it's not a phase. That's why we buried it here, right? And not, you don't want to put it here, okay? And by the way, you can get this just by, you can, this is how would you get this? C13, 0, S13 minus S13. And then you multiply with what? With with e to the I delta, 0 e to the minus I delta, something like this, am I right? Maybe not. Okay, no, sorry. Let me. I wanted to simplify things, okay? I'm going to contradict myself. No, forget it, what I wanted to say. We want to bury it in the middle, because that way there is no way you're going to use, you can try as much as you want to use this freedom, okay? But once I eliminate this thing, then the phase is only an overall factor. Equally on the row and the column.
Which can be added to the U.
Right, it's like multiplying with 2 to the I delta. You see what I did, and then with I to the minus I delta. And that will give me 1. Another thing which is very important, and I want to finish on that note, that if, okay, this is very important comment, I cannot let go. Imagine that the quark mass is a 0. Let's take up quark mass is equal to 0. Would there be mixing? Two generation. U bar, C bar, cosine, sine, minus sine, cosine, ds. But you see, if the mass is a 0, then I can keep rotating my states. How did I define these states when they became physical? By giving them a precise mass.
Yes, yes.
So in other words, they were like this. They were m up, u bar u, plus m down, d bar d. If this is 0, there is no way of defining that. What it means, that I can take uc goes into cs minus sc uc. It will be as good states. Notice the following. Not only if it is 0. Imagine that mu is equal m charm. Y and d. I needed charm. I wanted to talk about upwards. So this will be some m. Imagine m equal. Then you would have u bar u plus c bar c. Again, this is invariant under any rotation in the world. So in particular, I could, in other words, any linear combination of these states. Please, this is very important. This is crucial to understand, okay? The physical meaning of mixing. If particles are degenerate, there is no mixing. Just like the phases, it's not enough to have the mixing. It has to be such mixing that I cannot rotate by some symmetry operation, or by the freedom of my states. But you say, no, but I see the mixing. Okay, I invite you to compute. You will see that in this case, mixing will disappear. I'll show you that, but I won't do it today. In other words, I just want to emphasize this fundamental practical change. That any physical effect, when I calculate delta S equal to, whatever I calculate, will be proportional, without doing calculation, to sine squared theta Cavivo. That will be G Fermi, another thing. But there will always thing which is delta, it turns out it's the square of masses that enters. We will understand that. So what the G managed to do, it's not only to introduce the charm quark, they could predict the mass of the charm quark. Because m charm square minus mu square is very close to m charm squared. Mu is basically 0. And that's the greatest success of the theory. And you get that m charm is of 1.5 GeV. You predict it by doing this calculation. We will do that. I think it's worthwhile to do it either in the class with C or maybe in the guide. It's a reasonably straightforward, maybe with some tedium. Do you know how we compute it? There is nothing at 3 level, right? I killed it by introducing the charm quark, so therefore it will come at loop, and these two will come from well, there are diagrams like this, first to start. Z boson. If I put a W here and the W here, then I can change flavor. D, strange, because I can propagate up and charm. They change flavor. But this is 2 loop. At 1 loop, 2 W's. You must have thought of that. We'll do it. That's now, we can pause here. I needed this extra 15 minutes. So we spend some time on the Kano system and actually do the, or show the calculation at least. Question? Oh, that's totally my shit.